we will now investigate whether any conservative vector field automatically has a potential function. To do this, we will first slightly extend the definition of the curves that we consider to piecewise smooth curves. So this is the definition of a piecewise smooth curve. Let gamma from AB to U be a curve. We say gamma is piecewise ck smooth if we can find a partition P equal to T0 T1 Tm with the usual convention that A is T0 and Tm is B, such that gamma restricted to each Ti minus 1 comma Ti is ck smooth. Note, gamma could fail to be differentiable at the points Ti. Nevertheless, when you restrict gamma to Ti minus 1 Ti, this is going to be ck smooth. To understand the subtlety here, a picture is best to clarify what is happening. For instance, if you take a piecewise linear curve, that is just a polygonal curve, something like this. This is going to be piecewise C infinity. Why is that the case? Well, because when you restrict the curve to appropriate intervals, you just get straight lines which are C infinity smooth. So at this point, the curve is not differentiable. Even though one-sided derivatives will exist, they will not coincide. The velocity vector suddenly rapidly changes. Okay, so we can define integration on such piecewise smooth curves. So before that, let me just add one more thing to the definition. We will call piecewise C1 smooth curve as a path. Okay, a path is nothing but a piecewise C1 smooth curve, and these are also known as contours in complex analysis. These are the objects on which the complex integrals are defined, contour integrals are defined. So now let's define integration on paths. Definition: integration on paths. Let gamma from AB to U be a path, and omega a differential form on U, continuous differential one form. Okay, let P equal to T0 T1 Tm be a partition that comes from the fact that gamma is a path. From the fact that gamma is a path. Okay, we define the integral of this differential form omega. So let me just add continuous so that there is no confusion, to be the summation over I integral Ti minus 1 Ti not Ti minus 1 Ti integral over gamma restricted to Ti minus 1 Ti of omega. Okay, so we just break it up. We just break up the break up the interval AB into parts Ti minus 1 Ti, on which when you restrict gamma you get a C1 smooth curve. We already know how to integrate differential forms on C1 smooth curves, and you just take the sum. So as an exercise, show that this is well defined. Show that this is well defined. That means there are several partitions possible that makes gamma into a path, right? There is no uniqueness claim. How do you know that all of those breaking ups, all of those partitions are going to give rise to the same value of the integral of the differential form? Well, this exercise will tell you. Show that this is well defined. That is independent of choice of P. Independent of choice of P. Okay, so this is the definition of the integral of a differential continuous one form along a path. So I am not going to waste time proving which results are true for this more general notion of integral on a path. Let me just say that many things, including the fact that the fundamental theorem of line integrals, they are true for paths also, and I'm going to leave it to you as straightforward exercises in generalizing the same ideas. So I'm just going to remark that the fundamental theorem of line integrals is true for paths as well. Fundamental theorem of calculus is true for integrals along paths. That is, if you have a vector field that has a potential function, then if you integrate along a path, then the value you get is exactly the same. Of course, here I have defined only for differential form, so rather I should say if a differential form is exact, then the value of the integral along any path is just going to be the function's value at the endpoints with a negative sign in between. The same definition of path integral that we have given, integral along a path, can be given for vector fields also. It's a straightforward definition that I want you to do by yourself. So coming to the main theorem of this video, this is the existence of potential functions. Existence of a potential function. And the theorem is as follows: let omega be a continuous one form on a connected open set U subset of Rn. The following conditions are equivalent. The following conditions are all equivalent. Condition 1: integral over gamma of omega is 0 for all closed paths. That is, paths that have gamma of A equal to gamma of B. 2, the integral of omega along paths depends only on the endpoints. This is the next statement. And 3, omega is df for some differentiable function f from U to R. some not just differentiable from C1 smooth function, because we are assuming that the form is continuous. So we need C1 smoothness of this function f. Proof. Now 3 implies 1 is nothing but the fundamental theorem of calculus. Is the fundamental theorem of calculus. Theorem of calculus for line integrals. For line integrals. We have already shown this in the previous video. Okay. Now let gamma from AB to R be a path. Be a path. Define the reverse of gamma, denoted by gamma minus by gamma of A plus B minus T. Okay. Now I want you to sit down and think about this reverse gamma minus. It's certainly going to be a path because gamma is a path. But the interesting thing is it has the same trace as gamma, but it traverses gamma in the opposite direction. It starts from gamma of B and ends at gamma of A, as you can see. Okay. A straightforward computation shows that when you integrate a differential form along gamma, this is same as negative of integrating on the reverse of gamma. Oh, sorry, when you integrate a differential form omega along gamma, this is the same as integrating omega on the reverse with a negative sign. This is exactly like the one variable Riemann integral case. Integrating from B to A is negative of integrating from A to B. There in the Riemann integral case, this was just by definition. Here it is a consequence of the definitions of the path integrals. Okay. Now what we are going to do is we are going to concatenate gamma and gamma reverse as follows. Define eta from A comma 2B minus A to U as gamma of eta of t is by definition just going to be gamma of t if t is in AB, and it's going to be gamma minus, that is the reverse of t minus b, if t is in B comma 2B minus A. Okay. So this curve eta of t is also a path. Okay. And because the integral, this is going to be left as an exercise, the integral of a curve of a form on a path or rather the value of integral of a form on a path is independent of reparametrization. That is, if I integrate a differential form along a curve, along a path gamma, and I reparameterize gamma into another path, the value I get by integrating this differential form along this path is not going to change. It does not depend on the reparameterization. Now several things have been left for you to check. Check that this eta of t is also a path, and the next step will rely on this independent statement. Integral over eta of omega is nothing but integral over gamma of omega plus integral over gamma minus of omega. Okay, where does this gamma minus come from? Well, actually this part, the fact that this gamma minus of t minus b on b t 2b minus a is just a reparameterization of gamma minus, and the fact that integral along eta is just sum of these two is just by the definition of the integral along a path. Okay, now because of this expression, condition 1 is equivalent to condition 2. Fill up the details. There's very little to fill up actually. If you have a closed curve, you can just break it up into two curves. If you have a single curve, you can make it into a closed curve by this concatenation procedure I have shown, and from this you can actually see that 1 and 2 are equivalent. Okay, now assume 2 is true. Assume the second condition holds. Assume that the second condition holds. Okay, we now have to show that there is actually a potential function. So what does the second condition say? Let's recall. It says that the integral of omega along paths depends only on the endpoints. That means sort of in the vector field version, the vector field is conservative. Now we have to find a potential function. Here we have to find a function whose differential is this form. Okay, fix x naught in u. Fix it to be any point, it doesn't matter. Define f of x by definition to be integral of omega along gamma, where gamma is any curve or any path, that would be better, any path with endpoints x naught, or rather starting point x naught and ending point x, with starting point x naught and ending point x. This is well defined because we are assuming that there is independence of path. Regardless of the path, the value of the integral that you get by you integrate is exactly the same provided the endpoints coincide. That's the definition, that's the assumption in condition 2. Okay. Now the claim is that f is C1 and df is nothing but our omega. Okay. Now fix a path that joins x naught to x, say gamma from 0 1 to u. Okay, so fix a path. Now given any point in u close, let's not do this, let's be a little bit more careful. Consider the path that joins x naught to x plus h e1. E1 is the standard basis vector, the first standard basis vector. Consider the path that joins x naught to x by obtained by concatenating gamma with the straight line path t going to x plus t1. T is in 0 comma h. Okay, now you can concatenate these two paths and you will get a path. I'm going to leave it to you to actually define the concatenation. It's please refer to the previous parts to see how this is done. You get a path eta from 0 to b plus h, 0 to b plus h, 0 comma b plus h, sorry, 0 comma b plus h to u. That does the job. That is the concatenation. I want you to construct this eta rigorously. Okay, now by definition again, as in the previous parts, not parts, integral of omega along eta is nothing but integral of omega along gamma plus integral 1 to 1 plus h gamma of x plus te1, then the derivative, which is just e1 dt. This is just the definition. Okay, now f of x plus te1, sorry, he1 minus f of x divided by h is nothing but 1 by h integral 1 to 1 plus h a1 of x plus te1 dt, where omega is a1 dx1 plus dot 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 an dxn. This is again just by the definitions. Okay, taking h to 0, and applying the classical fundamental theorem of calculus, we conclude that the partial derivative with respect to x1 of f at the point x is nothing but a1 of x. Okay, similarly for the other partial derivatives. Hence f is c1 smooth on u and df is omega. So this concludes the proof of the fact that whenever you have independence of path, then you have a sort of potential function or a function whose differential is this form. So as an exercise, formulate and prove the above for vector fields. Exactly the same. Formulate and prove the above for vector fields. Rather straightforward. Let us now consider an example that will dispel misconceptions about the existence of this potential function. Consider the polar angle function on R2. This function is going to be given by arc tan y by x, at least on the first quadrant. Arc tan here is nothing but the inverse of the tangent function that you are familiar with. From basic trigonometry, you can see that this angle theta, the angle that is made by this vector connecting the origin to xy with the positive x-axis, is nothing but tan inverse of y by x, which I am calling arc tan y by x. Now this formula does not work for the entire plane. You will have to modify this formula slightly. So I have written down already what this function is going to be in detail. It's commonly called a tan 2 by symbolic manipulation packages like Maple or Mathematica. This a tan 2 of xy is arc tan y by x whenever x is greater than 0. That is on this right half plane. On this right half plane, this usual formula, the inverse tangent of y by x, works. If x is less than 0 and y is greater than or equal to 0, that is this part, then the function is given by arc tan y by x plus pi. If x is less than 0 and y is less than 0, that is this quadrant, that is the third quadrant, then the function is given by arc tan y by x minus pi. Now there's still some portions left. If x is 0 and y is greater than 0, it's defined to be pi by 2. If x is 0 and y is less than 0, it's defined to be minus pi by 2. And at the origin, it's undefined. So this function a tan 2, the range of this function, the range is closed minus pi to pi. Okay. Now you can check the above definition that a tan 2 is smooth, C infinity smooth on R2 minus the negative x-axis, x comma 0, such that x is less than or equal to 0. Okay, so on except this part, this function a tan 2 is actually going to be smooth. In particular, it's going to be continuous. Now intuitively, it is clear that there is no way to make this function, or no way to define an angle function that is continuous on r minus 0. Okay, there are several proofs of this. One of this is using winding numbers. There are several reasons why this is true, but intuitively it's clear that you cannot have a continuously defined angle function, polar angle function, defined on r2 minus 0. Okay, now let's see why this is true using the machinery we have developed. Look at the differential form omega, which is d of a tan 2. Okay, you can just do this differentiation and you will see that this is minus y by x squared plus y squared dx plus x by x squared plus y squared dy. Okay, this is just a straightforward computation in differentiating, so please do that. You will be able to get this. Note that this form omega is in fact C infinity smooth on R2 minus the origin. The only issue arises when the denominator x squared plus y squared is 0, that's at the origin. So despite the fact that a tan 2 is smooth only on R2 minus the negative axis, the differential form d omega is smooth everywhere except the origin. Okay. Now, as I keep saying, there is no angle function that's defined on the whole of R2 minus 0. But if omega had a potential function, or rather a function whose differential is this, that would be a candidate for a smoothly varying angle function. But omega cannot be exact. Omega cannot be exact. Why is that? Well, look at the circle. Look at gamma equal to cos t comma sin t as t runs from 0 to 2 pi, let's say. Okay, and compute, or rather let's just compute it at 0 to pi for the time being. So it's just the upper circle, upper half circle. Integral of this form omega along this gamma, it's just going to be integral 0 to pi sin squared t plus cos squared t dt, which is going to be pi. On the other hand, if you integrate it on the lower circle, on the other hand, Other hand, on the lower circle, for which we can take same function, gamma is cos t sin t, except t now runs from pi to 2 pi. You can check that now, let's just call this gamma 1 for clarity of notation. You can check that integral over gamma 1 of omega is minus pi. Okay, so there is path independence is not there. Path independence fails. Independence fails. So omega cannot be exact. There cannot be a single smooth function defined on R2 minus 0 such that the differential of that function is omega. So this gives another way of seeing that there is no continuously varying angle function, smoothly varying angle function that you can define on R2 minus 0. So this example concludes our study of potential functions. I have still left open the question of how exactly one finds potential functions, but that should be straightforward from the proof of the equivalence of three conditions that we saw. So there are some exercises that I have given in the notes. Solve those and you will understand how to find potential functions. This is a course on real analysis and you have just watched the video on existence of potential functions.